Hi viewers, welcome back to yet another video. In this particular video, the topic we are addressing is vibration measuring instruments. In the first place, let me ask you a question, or let's get started by asking this question. Why do we need vibration testing in the first place? Why can't we just do analysis or computer simulations and just keep quiet? But if you have a look at the industry, they do excessive testing for a lot of reasons. Let me cite a few of them. One is every computer simulation you run will have some kind of assumptions that goes into it. You know, a cantilever beam, if you take it, is a continuous system. But when we simulate the same in a computer, we assume the system to be a multi-degree of freedom system, where the degree of freedom, the number of degrees of freedom is finite, not infinite. So there are inherent assumptions that goes into a particular simulation. In order to improve the confidence with that particular simulation, it is better that you benchmark your simulation results with the test you conduct, so that you know what is the kind of error you can expect for a similar predictions in the future. The second point is to characterize a system. This is very important because often when we get problems in an exam, the mass of the system, stiffness of the system, damping present in the system, amount of damping present in the system, all these quantities are given. But once you start working and when you have a real life system in front of you to analyze, these things are not that pretty straightforward. You have to put your mind, you have to put your head into it, you have to think over it to evaluate this kind of system parameters. So vibration testing helps us a long way to evaluate these parameters. The other point is survivability. You can take an electronic package which is to be assembled to a launch vehicle. Then this particular package is going to see very severe vibration levels during its flight. So it should be proved that this particular hardware can sustain this amount of vibration levels. So the best way to do it is take it to a shaker or an electrodynamic shaker and then subject this particular hardware for the required vibration level. The other parameter which is of key relevance in modern era, where the average RPM or the average rotating velocity of most of the machine components are on the rise. We can see a lot of machines, turbo pumps operating at very high RPMs. Understanding the resonance conditions will help us to prepare for the worst conditions, because we know when a particular resonance can happen, and moreover the systems which are sitting close to our system of interest can be designed accordingly so that their resonances are separated by sufficient margins. So having said that, or having established the relevance of vibration testing, let me go ahead and discuss about vibration measuring instruments. Basically, vibration measuring instruments are transducers. Transducers, to put it in brief, they are systems which can convert a physical variable to a corresponding electric signal. There are different types of transducers. There are variable resistance transducers, then you have piezoelectric transducers, and you have electrodynamic transducers, and you have all kind of different transducers. I'm not getting into the nuts and bolts of all those stuff, but a basic vibration measuring instrument, let it be an accelerometer or a vibration pickup, the setup will be something like that. Let's say this is the it is bolted, or it is rigidly connected to the object whose frequency or whose vibration we need to measure. So let's say this is the portion of that particular body which is vibrating, and now we need to measure the vibration of this particular body. Let's say your body is vibrating with y of t, then you have a cage like structure over here, and in this particular cage you have a mass spring damper system, and let's say x of t is the displacement of this little mass. Then you have a small pointer attached to the mass, to this little mass, little m over here. Then the pointer, you have a scale also, so that this particular scale will read the relative displacement of the mass with respect to the body. So let me put it down here, I think that's better. So this is the body which is vibrating, and this is the little mass, which is obvious. This is the little mass. This can be also called as a seismic instrument, and this scale measures the relative displacement, which is z of t, which will be nothing x of but x of t minus y of t. So that will be your relative displacement. Okay, well and good. So I haven't shown the transducer in this particular figure. So this is a basic outline of a vibration measuring instrument. Now let's go ahead and use the principle whatever we have learned to understand in detail how a vibration measuring equipment really works. So we just saw that a seismic type of instrument as shown over here will measure the relative displacement. Now in the next section we are aiming, or we are trying to represent or establish an expression for this particular relative displacement. So let's go ahead and do it. The first step in doing so is to draw the free body diagram for the little m over there. So as shown here, the little m is acted upon by two external forces. One is the spring force and the other is the damping force. Using Newton's second law, I can write this particular equation, mx double dot of t is equal to these two forces basically. The spring is seeing a relative displacement of x minus y because your body is also moving, or in other words, by whatever amount this body moves, the same kind of displacement is felt by this portion of the spring as well. So the relative displacement in the spring as well as in the damper is x minus y. That's why this quantities looks the way they are. And x double dot of t is the acceleration of this particular mass. Now I am bringing in substitution. I need to compute what is the relative displacement, or I need to get an expression for the relative displacement. So I'm bringing in some assumptions, not some assumptions, some change of coordinates you can call. I'm putting z is equal to x minus y. Then some simple maths, z of t can be written as like this because they are functions of time. As time progresses, the displacement of the vibrating body is changing. So it makes sense to to assume them as functions of time. Similarly, first derivative of z of t and double derivative or the second derivative of z of t is evaluated as shown here. Now, plugging these equations back into the equation we derived after applying Newton's second law and doing some kind of mathematical jugglery, we are here. So this is the final equation we have to deal with. This equation pretty much looks like that of a force vibration equation, where the excitation term is slightly different. That's it. It is minus my double dot of t. So assuming that y of t assumes the shape like this, given in exponential form, then y of t can be written like this and y double dot t can be written like this. Simple algebra once again. In my earlier videos, I have explained elaborately what are the advantages of working with complex notations. So I'm not going to repeat the same over here. If you want to listen to those videos, listen. If you want to know about these things, you can watch my earlier videos. Now, so this is the kind of excitation. Now, we can assume that since the excitation force is changing, is having a frequency of omega, the response will also have the frequency omega. So that was in words. Now putting that into an equation, we can assume that z of t, the variable which we are looking at, can be assumed as capital X. That will be the amplitude, capital X e raised I omega t. The key takeaway is that this particular omega and this particular omega are the same. Now we have an assumed expression for the relative displacement z of t. So z of t is equal to capital X e raised I omega t, where capital X is the amplitude of the relative displacement. The first goal is to arrive at an expression for this capital X, which is the amplitude of our relative displacement. So how to do that? This was the equation we got. Now substituting in this particular equation, we will reach here. So this is again simple maths. I'm doing nothing else. Y double dot of t is also substituted from here, and once we do all those substitutions, then we will reach here. It's simple maths, nothing else. So the amplitude of relative displacement is obviously a function of the amplitude of the vibrating body and some other system parameters like mass of the system, then the frequency at which your vibrating body is moving. Now can we bring this simplified further down? Yes, we can. So in the next few steps we are going to do this. In the first step, take this little m or divide both numerator and denominator by this little m, then we are here. As a next step, and in between we know k by m is omega n square, and now can we write c omega by m another way? Yes, we can simplify it further down. So the amount of damping present in the system can be always written as the damping factor times the critical damping coefficient. So that is what we are done here. Then critical damping coefficient for a single degree of freedom system can be written like this, 2m omega n. So finally this particular term over here can be replaced with this. Then this is the magnitude of, or this is the amplitude of the relative displacement. We will further simplify it by dividing both numerator and denominator by omega n square. So we are here. Once we do that, here is the final expression which we were looking at for the amplitude of the relative displacement, where r is the frequency ratio given by omega n, and zeta is the damping ratio, c by cz, and capital A is the amplitude of vibration of the body onto which this particular vibration measuring instrument is fastened. So now we have an expression. Finally, we were looking at z of t. So z of t is capital X e raised I omega t, and now we have completely found capital X in terms of all the non-system parameters. If you apply your mind a little bit further, you can see this particular amplitude capital X is a complex number. That means it has a magnitude as well as a phase. If I write it like, if I write the complex number capital X in this way, like capital X is equal to, let's say, mod X, which denotes the magnitude, and e raised minus I5, then Since this is the complex number right over here, the magnitude will be mod of x will be ar square, the numerator as such, and in the denominator root of 1 minus r square whole square plus 2 zeta r whole square. And what will be 5? 5 will be, I'm not going into the detailed derivation. I have shown this also in one video. This will be tan inverse of 2 zeta r divided by 1 minus r square. So everything is completely known. Now if I finally write the expression for z, then it will be modulus of x times e raised I omega t minus 5. So there is a phase lag for the relative displacement compared to the displacement of the vibrating body. Now the next question is how these two parameters, so the whole response is governed by one thing, which is the magnitude of one is the magnitude and the other is the phase. How these parameters vary with respect to our r, which is the frequency ratio, that is the topic of discussion in the next segment.